Hello everyone, and welcome to the first video in our Meteorology Summary series, where we break down key concepts to help you ace your aviation exams. Today, we're diving into the first subchapter, composition, extent, and vertical division. By the end of this video, you'll have a solid understanding of the atmosphere's structure and be ready to tackle any related questions. Let's get started. The troposphere is the lowest layer of our atmosphere, extending from the Earth's surface up to the tropopause. It's the layer where most of the atmospheric humidity is concentrated, making it the primary focus for weather and aviation. For aviators, the troposphere is crucial because it's where most of the weather phenomena occur. Within this layer, there is an overall decrease in temperature as altitude increases. However, its thickness varies depending on latitude. It's thicker over the equator and thinner over the poles. For example, the troposphere extends higher in equatorial regions than in polar ones. To put it in numbers, the troposphere contains over 90% of all water vapor and the majority of the air. Its composition, in terms of dry air by volume, is approximately 78% nitrogen, 21% oxygen, and a small percentage of other gases. Next, let's move up to the tropopause, the boundary layer between the troposphere and the stratosphere. This is a fascinating region with unique characteristics. For instance, the tropopause is defined by a minimal temperature change. It ceases to fall with increasing height, specifically, less than 2/3 of 1 degree Celsius per 1,000 feet over a range of 6,000 feet. The average height of the tropopause varies with latitude. Over the equator, it's typically around 16 kilometers, while in mid-latitudes, it's closer to 11 kilometers. It's important to note that the tropopause isn't a continuous surface. Its height and temperature fluctuate. For example, the temperature of the tropopause in polar regions is higher than in equatorial regions. In the tropics, it's not uncommon for temperatures at this level to drop to -75 degrees Celsius or lower. An appropriate temperature at the tropopause, located at a height of 20 kilometers, is -100 degrees Celsius. The temperature lapse rate changes abruptly at this boundary, marking a significant shift in atmospheric behavior. In the northern hemisphere, the height of the tropopause decreases from south to north. For instance, the tropopause at 50 degrees north is lower in winter and higher in summer. While the ISA assumes a tropopause height of 11 kilometers everywhere, real-world conditions tell a different story. The altitude of the tropopause decreases, and its temperature increases as we move from the equator to the poles. Consequently, the tropopause is lower over the North Pole than over the equator. In the tropopause, the only significant observation is a change in the temperature lapse rate. In tropical regions, the tropopause height is typically well above the flight levels, making its height less critical for flight documentation. From an aviation perspective, the tropopause brake's position is significant because jet streams are often located near its brakes. It's worth dispelling a common misconception. Air temperature does not fall severely above the tropopause. Let's break this down further. At 30 degrees north, the tropopause is generally around 38,000 feet, but can reach 50,000 feet during the summer. At 50 degrees north, it's typically around 35,000 feet, dropping to 28,000 feet in the winter. At 60 degrees north, it's around 30,000 feet, but can fall as low as 25,000 feet in winter. Typical heights and temperatures include equatorial regions, 50,000 to 60,000 feet, with temperatures ranging from -60 Celsius to -80 degrees Celsius. Mid-latitude regions, 35,000 to 40,000 feet at around -55 degrees Celsius. Polar regions, 25,000 to 30,000 feet at approximately -50 degrees Celsius. The tropopause is significant for aviation because it marks the maximum height of clouds, the location of maximum wind speeds, the presence of jet streams, the potential for clear air turbulence. From an aviation perspective, understanding the tropopause is key to anticipating weather patterns and flight planning. Above the tropopause lies the stratosphere, a stable layer extending roughly from 11 to 50 kilometers above the Earth's surface, in mid-latitudes. This region is notable for its lack of weather activity and clouds, making it relatively calm compared to the turbulent troposphere. The stratosphere is home to the majority of the ozone layer, which absorbs harmful ultraviolet radiation. In the lower part of this layer, the temperature remains relatively constant with altitude. However, as you ascend further, the temperature begins to increase due to the absorption of UV radiation by ozone. This stability makes it an ideal cruising altitude for many aircraft. At the top of the stratosphere, we find the Stratopause, located at around 50 kilometers above the Earth's surface. Here, the temperature stabilizes again, marking the transition to the next atmospheric layer. While not directly relevant for typical flight operations, it's an important part of understanding the atmosphere's overall structure. Now let's take a broader look at the atmosphere as a whole. It's composed of nitrogen, oxygen, carbon dioxide, and argon, with water vapor playing a crucial role in weather. Interestingly, the concentration of these gases remains constant up to a certain altitude, except for water vapor, which varies. Nitrogen makes up the largest part of the atmosphere by volume. From a meteorological standpoint, water vapor is the most significant gas because it directly influences weather conditions. However, during flight, ozone can pose challenges, as it may irritate the skin or eyes when encountered at cruising altitudes. The air consists of various gases, but the most harmful gas encountered during flight at cruising levels is ozone. The atmosphere is split up into layers according to the vertical temperature profile. Additionally, there is great potential between the Earth's surface and the ionosphere, because the electrically charged particles between the ground surface and the ionosphere have different distributions. Understanding these details helps us appreciate the atmosphere's complexity and its impact on aviation. Thank you for watching this video on composition, extent, and vertical division. This video focuses on the key theory points you need to answer database and exam questions efficiently. I'll be posting a second video dedicated to practical exercises for this subchapter, so stay tuned. If you'd like a more detailed explanation of any topic, let me know in the comments. Also, don't forget to join our Reddit community, where you can ask questions, share doubts, and request exercises. Let's simplify aviation studies together. See you in the next video. And if you found this helpful, don't forget to like, subscribe, and turn on notifications so you don't miss any future videos.